Okay, sorry about the delay. So yeah, extending the LISP model from const cells to triples and from trees to hypergraphs. And my colleague Ray is not here today, so I speak for both of us. So we're talking about something called Arkana, which has been circulating by us for over a decade now. We've given different talks in different places, but we came back to it recently with a completely new application. So probably everyone here knows what a const cell is. So you have a car and a cdr. It's these two things you stick together to make Lisp objects like trees and S expressions. So what if instead of two things you had three? Just this other thing, which we're going to call text, sitting there floating in the middle. And you could build structures out of those things. And suddenly now, instead of having things that look like trees, nested S expressions, you have things that look like graphs with edges. Except they actually look like hypergraphs because in the semantic web terminology, each one of those triples I mentioned is reified, or as Ray likes to say, reified. So what does that really mean? It means you can point to an edge as well as having an edge connecting two nodes. So there's a little diagram here. Your regular looking edges are in faint green. John loves Jane. Jane is married to Jim, etc. But what's this weird thing in blue? John disapproves of perhaps the fact that Jane is married to Jim. And Mom resents the fact that John disapproves that Jane is married to Jim. So you could probably represent this kind of data structure using a good old standard semantic network without this weird pointing at edges stuff. You just say married, you'd have it sort of have this correspondence between the edge married and the sort of Jane married Jim node or something, but it would look actually complicated. So this seems weird, but the alternative is probably even worse. So this is the kind of data structure we're working on when we say hypergraphs. Some people call this polygraphs, which is a weird kind of joke, I guess, name. But anyway, we'll call them hypergraphs for the purpose of this talk. So what can you do with these these things? So just to make it even more fun, we've given everything a new name. So instead of calling it an edge, we're going to call it a NEMA. Because we use the same data structure to represent nodes and edges. It's kind of this computational slush. So those things, which you can just think of as an edge, are NEMAs. And if you put all of them in one big bucket, that's called a plexus. So a plexus contains a bunch of NEMAs. That's basically your semantic network. And these things also contain a distinguished ground element. And so let's make an example similar to the diagram. If I have a NEMA ADE, let's call that alpha for short, then I can say alpha CB, and I'm now making an assertion about that link, alpha, right? So I say alpha has property false, or alpha has property added by Joe, whatever. So I'm now annotating the link. But supposing I wanted to annotate just the beginning of that link. Maybe ADE is Joe is in Oxford. Or Oxford is hosting ICFP. So I want to say get source alpha, because alpha, that's Oxford. And I want to make assertion maybe to say DE, in this case now I'll say in 20, let's see, as assertion about Oxford. Well, Oxford, the city in England as opposed to Oxford, Mississippi, right? So I want to make this assertion about that particular Oxford in that triple. That's what you can do with this get source thing. And I'm now illustrating in this part something a little bit weird, which is instead of just having objects that are like static things like Mom and John and Jane and such, I can also nest code inside of these things, like with your const cells. And then the last thing is, supposing I wanted to actually make an assertion about A itself. Well, this is what I said before. You can represent these things as NEMAs. You just put ground in there in the appropriate place. This has no source and no sink. That's A without a source and sink. This is Oxford, and so then I can subsequently make an assertion about that place. Standalone. Okay, so this is the basic mechanics. And there's the fact that these things are mutable. I mentioned this in the slide. This sort of means that basically, if you don't want them to be mutable, don't change them. So that could be helpful, but they are mutable kind of by default. So what do you get? I mentioned some of these things in overview, but this is a lightning talk, so I'll try to have lightning strike twice. So yeah, you can represent these hypergraphs rather than trees. You can put code inside of your graphs or hypergraphs, which is different from a mainstream graph database, by the way. So that's the kind of killer app here. And that allows you to build runnable models using these complex recursive structures. E.g., and I'll show you this in a minute, if you want to model mathematics, especially informal mathematics as opposed to fully formalized mathematics, you can. And there's a bunch of related work out there, some classic stuff called Flare, which I think never really took off, and Zigzag, which I think at least halfway took off. But a more recent thing is called Atom Space, and that's like everything we do but better, except much more complicated. So they instead of NEMAs, they call them atoms. It's the same kind of logic, and they've got scheme and Python bindings, and they've got different optimizations and all kinds of stuff. So if you wanted to use an industrial thing, maybe Atom Space is the right way. But for us, Arkana is great, and it just lets us keep hacking, especially because we've been doing this super sub part-time for over a decade. It's nice to have something that's not too complicated, doesn't have a bunch of changing dependencies, just depends on Emacs Lisp, actually. And so yeah, here's the history. The first talk about it was in 2005 with a really great demo. I don't think we've ever given such a great demo since then, because after that we started tinkering around with the back end. So first it was just Emacs, then I rewrote it to have a bridge to Common Lisp. At that time, this was just to use the Common Lisp interfaces to different database backends, which I think now you could just do in Emacs. But in 2013, Ray created the backend that we're using now, which is this kind of built-in triple store with those things stored in hash tables. So we presented in New York. I talked about it in London a few years back. And Ray just talked about this related stuff in New York again. And next Saturday, I'll talk about the application to mathematics here at Farm 2017. But yeah, just because you might want to see what it looked like back then, this is a screenshot of the 2005 edition running this morning on the bus, no strings attached. What you could do with that is you could annotate some text. So I built this kind of browser, so you can go backwards and forwards like with your Lynx browser or EWW. And instead of just browsing things, you can also annotate things, and you could annotate annotations. But this didn't use the same backend, it just used a slightly different backend. But you can see the sort of thing you could do with it is build a model of a document. In this case, it's a LaTeX document containing literate source code for the program. That's incidental. And then you could add annotations and browse around in this kind of way. And we called it a Scolia-based document model for Commons-based peer production, because the idea was people would add things. A scholium is like an attached footnote, and the thought was everything grows by attaching. And you could think Git kind of does that. Everything grows by attaching in this DAG. So this was like Git before it was Git, kind of. And then if you want to go even further back, we didn't invent this at all, but some inspiring thing for the latest round of work is this thing called conceptual dependence theory, which was created by Schenk and others for story understanding. So if you wanted to represent John gave Mary a book as part of your story, that's the graph, and then that just becomes a nice little frame in Lisp. And we view these things as analogous to performatives, which I'll show you right now. So here's a little graph from the mathematics application. So people are having this discussion, in this case is on Math Overflow, about some mathematics. This should be a sort of motivating example. Why do we care about graphs and edges? Well, we modeled this up using a nice modeling language of assertions and some discussion of the content. So someone says this, they build up this structure, and then someone else comes along with a new set of edges and things, and they say, wait a second, you made a mistake in your notation. So this is the sort of thing, and these graphs grow by attaching, lots and lots of attachments. So I'll just show a little bit, the first thing, and in fact just sort of simplifying it so that I took on board the correction, so you just see something that actually makes sense. Someone asserts you know, if you've got this conjunction, a finite group as a subgroup, the subgroup has this property that's finite, then it's not equal to the union of these cosets. So what would that look like inside of Arkana? Well, it looks an awful lot like the S expression I just gave you. Each of those things that becomes a node gets a number, because that means it's stored in this graph thing as a unique node, and it in this case has some content. Some of them have some content which is pushed in, and you have to imagine for yourself what that structure looks like, but it looks an awful lot like the slide I just showed you. You get this back as a handle to all those objects which you've created in the back end, so that you can then add new structure relative to the existing structure. And here's what that looks like kind of as a schematic. So next Saturday we'll talk more about what you get and what you can do with this kind of stuff. So here's another little bit of mathematics. Square root of 3 minus square root of 2 to the 2012 is small. We claim that this idea implements another strategic point. Numbers close to integers have 9s in their decimal expansions. What the heck does that mean? Well, if you look under the hood, you've got these triples floating around. Here's a triple there. Here you've got some more on the other side, some triples pointing to other triples, so you get these kind of stacks of nested structure inside of things, and then even in the middle of the node you've got some program logic there, which in this case is going to compute a certificate to tell you, yes, this thing on the left really does implement the idea expressed, strategic idea expressed on the right. So that's for Saturday. Here's a summary because it was a quick talk. So what do you get? Local storage of code and data, well, you already had that in Lisp. Triples add content to your const cells, so that's sort of like a property list. Imagine your const cell has this extra property, which is content. But graphically, it allows you to then think of these things as graph-like structures. Code can then act on the structures, like in Lisp, so you can reason about these graph structures. And nested code can be used to create overlaid structures like this cone I've drawn on the left, and that's sort of like Emacs text property but attached to a graphical structure as opposed to a linear string of things in buffers. So that's it. Oops, no, it's not quite it. It's almost it. It will be after we do all this future work. So we'd like to formalize the spec because we think actually some of the stuff about reasoning about these edges, especially if you allow variables, you can get a very interesting sort of alternative to lambda expressions built out of these NEMAs. But even just formalizing it so that the back end itself is on solid foundations would be good. So yeah, there's been these different versions. So one of the slow-going projects is to integrate all of the old features. We've designed and sort of spec'd out some code libraries for things like searching and interaction with these cones, versioning, typing, and all of this stuff, all these great features would allow us to basically create an actionable digital library. Wouldn't it be nice if we could integrate with some external databases and work with large data? So yeah, the fact that we're using a Lisp backend is good for the programming, but if you wanted to just manage a whole lot of data programmatically, you would want to have some alternative backends. And then maybe one of the more interesting things for this group is we'd like to integrate features from the reason schemer to reason effectively about the objects. So that's really it for this talk. But yeah, let me just recap one last thing about for Saturday. Reasoning, as I said in the last thing, is reasoning about the graphical structure. So if you've got a graph, you might have some inference rules that says, oh, I see this pattern. Well, I know from my graph grammar that I can replace this pattern with that pattern. So basically the reasoning is all about finding patterns in graphs, transforming them, and yeah, that's all I have to say. We have a Git branch which you can actually just go on and edit if you want to, because it's got public permissions. And yeah, you can also email me or Ray, both of us. So that's it.